The next topic I want to touch on that had a couple of missing pieces in the previous video has to do with Dalton's law of partial pressure. Now, as described in the video, Dalton's law of partial pressure says that the pressure of a mixed gas is equal to the sum of the pressure of each of the gases individually. So in the video we talked about that nitrogen makes up about 78% of the pressure. Nitrogen is a filler gas. We do not use it for anything that keeps us alive. But it comes in very handy. We'll talk more about that in Respiratory 140, of why it's important. Oxygen makes up about 20.95%, or we say 21%. Argon makes up about 0.93%. So these three were covered in the video. But the one gas that he didn't cover that's very important to us is carbon dioxide. Carbon dioxide makes up 0.03% of the partial pressure in the atmosphere. And when we get into Respiratory 120 in the spring, and we're talking about how we breathe and the pressure differences, you're going to see where this comes in and is very important for when we're breathing. All the other trace gases, helium, neon, all make up 0.01% of the atmosphere. So, what is the actual pressure? Well, to determine the actual pressure, you have to take the percent, divide by 100, so you have a decimal point, and multiply it by the atmospheric pressure that you know. So at 1 atmosphere, at sea level, we're going to take nitrogen, 0.78 times 760. We're going to take oxygen, 0.2095 or 0.21 times 760. Argon will be about 0.0093 times 760. Carbon dioxide is 0.0003 times 760. And the trace gases, 0.0001 times 760. Now, the pressure of all of those gases individually has to equal 760 millimeters of mercury. So when you do the calculation, nitrogen comes out to about 593. Oxygen comes out to about 160. Argon comes out to about 7. CO2 comes out to about 0.23. And the trace gases make up the rest, 0.076. So you may say to yourself, again, Dr. Allmiller, that's all interesting and fascinating, but what does that mean to me? Well, the oxygen pressure is extremely important to us because, as you will learn in Respiratory 120, if that pressure goes down, it gets harder to get oxygen into your bloodstream. And so patients end up, or people end up, with less oxygen in the blood. So we need to be able to calculate what the pressure of oxygen is given the current atmospheric pressure. So let's look at a calculation. What is the partial pressure of oxygen at Pikes Peak in Colorado? Now, if you've never been to Pikes Peak, it's wonderful. I've been there multiple times, and it's really good. I do get altitude sickness. We'll talk about that in Respiratory 120. Now, the height of Pikes Peak is about 14,115 feet, or 4,300 meters above sea level. And the average barometric pressure at Pikes Peak is about 450 millimeters of mercury. So how do we figure out the pressure? Well, we take the barometric pressure that we know, 450 millimeters of mercury, and we multiply it by the gas that we're looking for. In this case, we want to know the partial pressure of oxygen. Well, we know that it's 0.21. Okay? And that comes out to 94.5 millimeters of mercury. That is about 40% less than the pressure at sea level. So if you have somebody who already is predisposed to respiratory problems, they have emphysema or bronchitis, bronchiectasis, whatever, this can have a major effect on them. Now, I used the extreme of Pikes Peak, but it could be anywhere. Somebody travels and it's 3,000 feet above sea level. You look at the barometric pressure and see what is going on. We get this in the hospital. When a low pressure system comes in with weather, the barometric pressure drops. I always say, I can tell you what's happening outside with the weather just by seeing what type of patients are coming into my emergency room. Because when that barometric pressure drops, because we have storms coming in, all of my COPD patients can't breathe. And so they're coming in. So this is a very important concept that you have to be able to understand. The last piece that I want to touch on is about acid-base balance and regulation. You are learning the basics about acids and bases, and you've already learned about strong acids, weak acids, strong bases, weak bases. But I want you to understand that nearly all of the biochemical reactions that occur in your body influence the acid-base balance of the environment in which they're in. Now, it was already covered in the video that a normal arterial blood pH is about 7.35 to 7.45. So it's very slightly on the alkaline side. An alkalosis, as was covered in the video, is anything with a pH above 7.45. And an acidosis, again, as covered in the video, is anything below a pH of 7.35. Now, the majority of the hydrogen ions, which is the acid, that's what the pH scale measures, remember it's the power of hydrogen, originate from one of four things. The breakdown of phosphorus-containing proteins. So when your body is breaking those down, it develops phosphoric acid. Anaerobic metabolism of glucose. If you lift weights or you do a lot of workout and your arms are really sore or your legs get really sore, that's because you probably went into lactic acidosis. You were not getting enough oxygen to meet the demands. The metabolism of body fat. We are constantly creating and burning body fat. So this creates fatty acids and ketone acids. And the last part is actually the transport of carbon dioxide in the blood as bicarbonate. And what happens is it liberates a hydrogen ion, which affects the pH. Under normal conditions, the hydrogen and the bicarb ion concentration in your blood is regulated by three major systems: the chemical buffer system, the respiratory system, and the renal system. Now, the chemical buffer system acts within fractions of a second, and this helps to resist any rapid or wide swings in the pH range as this acid is being produced or released. This is our first line of defense. And the system is composed of carbonic acid bicarb buffering system, the phosphate buffering system, and a protein buffering system. Now we're going to get more involved in that in Respiratory 120 next semester. The second system is the respiratory system. Now the respiratory system acts within about 1 to 3 minutes. So if the chemical buffering system is a little overwhelmed, the respiratory system is going to kick in. And it will increase or decrease your depth of breathing and your rate of breathing to offset any acidosis or alkalosis, respectively. Basically, we're controlling the carbon dioxide. So we're either retaining more carbon dioxide, which creates carbonic acid, which will then lower the pH, or we breathe faster to get rid of more carbon dioxide, less carbonic acid, to raise the pH. And the third system is the renal system. Now, the renal system is the most effective acid-base balance regulator in our body. The problem is, it's also the slowest. It can take a day or more for the renal system to correct an abnormal pH concentration. So if your chemical buffering system gets overwhelmed, the respiratory system starts to pick up the slack. But if the respiratory system is broken, or it can't keep up, then your kidneys are going to kick in. And they're either going to hold on to bicarbonate, or they're going to release acid into the urine. We are the experts in acid-base physiology as respiratory therapists. And next semester, we're going to go a lot more involved with it, and we're going to be talking about how to interpret arterial blood gases and what is happening in your patient. So to fully appreciate this balance and how it's regulated, you have to have a fundamental understanding of acids and bases and their influence on pH. And that's why the video talking about strong acids, strong bases, weak bases is so important. This is the last video for this unit. We will next be moving on to Unit 5.